Danny's asked me to talk specifically about the farm model, which is going to set up some of the talks we're going to see later. Certainly from Mohammed, who's been doing the calibration work on this, and Chris is going to be talking tomorrow about some of the underpinning data that we're using to try and develop the farm model. I'm assuming that one. There's a sort of a cast of thousands on this who have been involved in it. Technically, it's myself and Mohammed, I think, are employed on ad trees on this, and Chris and Matia, who has now left us to take a faculty job, are working on it on the Net Zero Plus project. So the first question is why do we need a farm model? It depends on what questions we're trying to answer with this, but certainly for the sort of analyses that Danny was talking about earlier, one of the things that users are interested in is what they're losing out on if they're going to be planting trees. So what are they losing out on if they're taking land out of agriculture, putting it into forests, in terms of food production and in terms of farm profitability? So that's going to be an important thing. There are other users who we're working with, particularly DEFRA or maybe other regional decision makers, who want to know things about, well, what if I want to encourage people to plant trees? What sort of incentives am I going to need to pay them? So the farm model is a tool through which we'll be able to work out which farmers might be likely to take up incentives in which areas in response to which sorts of policies. So this farm model is going to be a critical part of that sort of tool as well. And in some ways that's more down the Net Zero Plus side, but it is a problem I think quite like to get a handle on without trees. And there are, certainly for that policy group, a bunch of questions that the farm model is going to help us answer, such as the consequences for farm incomes, farm viability and food security of taking land out of agricultural production and put it into trees. So this farm model is quite critical to a number of questions that are going to be important for our users of different scales. Why do we need a new farm model? Well, we had an old farm model. That old farm model was based purely on data. It was econometric, but it had certain faults in it. One in particular was that it wasn't particularly well calibrated to data. It didn't have underlying structural representations of crop growth or of livestock productivity. So that model I'm going to refer to as the old farm model. You'll see a little bit of our research on it that we've been using the old farm model, which the new farm model will try and take over. There are other farm models, but they're not available to us. So Cranfield have a farm model that CH has used. It's a linear program, quite detailed, not easy to use for certain problems that we want. But we need our own one. We need a new one to be able to do this, and that's what I'm going to talk about, the new farm model. So it's a structural model, which in economics means it tries to describe the underlying processes, and not a statistical model, which is trying to match data to particular inputs. And we're going to think about the model as starting off with a farm. It's going to be a farm level model. We've got an initial farm capital, barns and machinery and things. And what the farmer's doing is choosing their activities and their investments in order to think about optimizing some intertemporal expected utility from food production. Farms are much more complicated than that. They have a whole bunch of other things going on, Airbnb and I don't know, some maze or something, all those other things that farms do. A farm shop, we're not dealing that. We're just thinking about the food production. It will be, it's difficult enough just to do that. And what does the model come out with? Well, it comes out with potentially uncertain or distribution, time series of the land use and management choices that are made over each of those parcels that Danny was showing us, which are under agricultural land for this farmer. And it tells us something about the farm profits. And what do we need it to do? Well, it's got to respond to changing climates and weathers, changes in the prices and costs of various agricultural outputs and inputs, schemes which try and incentivize in different ways what farmers do, particularly planting of trees, and legislation which stops them doing things or putting too much fertilizer on. So the model's got to take these sorts of inputs and give us these sorts of outputs. A quick terminology for you. We're talking about parcels. You might think about fields. That just happens to be the terminology that's used in agriculture. There's a lot of them, 2.5 million across England. So as we start thinking about scaling these models, it becomes quite difficult. The model's working at the scale of a farm. and we have, through Chris's work with DEFRA, access to the actual parcels which make up a farm. Farms are of different types. So they might specialise in cereals, they might specialise in dairy, they might have a mix of those things. And on each of the parcels, farmers undertake an agricultural activity, which could be one of these crops, or it could be sheep, dairy, cattle, different rotations. Okay, so those are the sorts of terminology I'm going to be using. So this is how the farm model works. And if you think about it in the order in which we might imagine a farmer thinking about it, they make an annual decision over farm capital. So farm capital is the stuff that you need to be able to do stuff. If you want to change what you're doing, you have to change your capitals. And they're thinking of expanding barns or milking parlours or getting new tractors. So that's the first decision. It determines the range of possibility as to what you can do on your farm. Given the capital that's available to you, you're then making a decision about what activities to do on your different farms. What sort of crops should I put where? How should I stock my livestock across the grasslands that I have in the farms? And then once I've decided what I'm doing where, these are actually simultaneous, but what I've decided to do where, I've got to think about how am I going to manage what I've got on my, what parcels I've got on my land, how much fertilizer I'm going to put on, when am I going to put it on, when am I going to sow my crops, how many head of cattle I'm going to have across my grassland. So we've got these management decisions. If you think about how we solve it, working backwards is how the model solves out. We think about, well, what would be the best way to manage each parcel across all the different things I could be doing on it. Once I know that, I can then think about, well, what would be the best mix of things to do across the parcel to get the best outcome from the farmer. And then we can think about, well, what sets of mixes would be best from the capitals. And I think about all the different capital investments I can make. This is the solution. So let's start at that first part, the parcel management model. Now, this is the core, the driving heart of this model, how people are making decisions about what to do on the land, and therefore the profitability of each parcel under different activities. So we've got a farm, those are the parcels on the farm. There's a parcel, and I can choose an activity. That's maize, this is wheat or something. And we're thinking, given a parcel is used in a particular activity, the thing we've got to do is think about how that parcel can be managed, and therefore what benefit it will bring to the farm business. That's what these parcel management models are doing, these core driving motors of the farm model. There's two of them. One is thinking about how am I going to manage this as an arable, so that's growing crops, and how am I going to manage it if I'm using it as grass in order to support my livestock. Oh, I've got an equation down there. The work so far has focused very much on this part of the model, so the arable management component. And underpinning it is a biophysical model of crop growth, which is called WOFOST. I can't remember what that stands for. This is one that's used widely in the agricultural modelling community. So that's a structural model, and it gives you a daily time series of growth of the plants and final yields of the crop that you're growing, given a series of inputs. We're running this model at a parcel scale, which are index I, and that parcel has got an area of HI hectares. And what goes into this model? Well, first off, you've got to tell it the crop type, which we're going to label as J. We've got a set of qualities of the parcel itself, these soil parameters. We've got a weather time series, and we've got to make a series of farming decisions, these management decisions, which I'm going to label X, such as when I sow the crop and when I fertilise and the quantity of fertilisers I put on. Those are the management decisions. And once I've got that, this model, I've given all this information, that gives us the annual yield in that particular crop. So this is what the WOFOST model is doing for us. So once we've got that WOFOST model, we can then start thinking about what the profitability is for the farm. So given I've made some management decisions X under a particular weather time series, given the qualities of this particular soil and the parameters of this model which describe the crop, I get some production. I can multiply that up by the price of that production, by the per hectare production and price hectares, and I get the amount of revenues I've made minus some costs associated with doing that. So this is the profitability. We could add on an error term here, uncertainty over what this production is. We could add on other motivations. I'm going to leave that at the moment. At the moment, we're thinking about this as purely profits. Now, one of the things we want to introduce into this model is the idea that farmers are risk averse. And this utility function picks up the idea that farmers are risk averse. They might have preferences over sets of management which, under uncertainty over what might happen in the future, tend to favour things which give you a reasonable return rather than ones which have chances of really low returns offset by chances of higher returns.
So this tends to be true, Brett, historically.
Yes, so there's a lot of empirical evidence. This parameter here catches that risk aversion, and if you look at the sort of range, if this parameter was 1, you would be risk neutral. We'd say in farming that parameter could be between 2 and 5 is what the empirical data's looked at, but it depends which farm. So if you're a big farm, you can do lots of things which can spread your risk. You're not so risk averse. If you're a small farm, potentially this can be high, but we're planning to try and estimate this from the data. This is going to be calibratable, so any of those could be happen. So we've got this risk averse utility function, and the uncertainty really is over what weather I'm going to experience in the next period. There are other uncertainties, that's the one we're concentrated on. Now, actually, in reality, the decision process is quite complicated for farmer, because at each period in time, they can adapt their decision as they learn what's going on. So we read out what that problem was, decided it was too complicated, and came to something an awful lot simpler, in which farmers are choosing management strategies. It should be X's, not M's, sorry about that. And given a management strategy, there's a set of possible weather conditions which will lead to a set of possible profits. So I'm trying to choose the management strategy which gives me the most expected profit or expected utility because of that risk averse thing, given the different weathers that might arise. So again, in the pursuit of simplification, while the data science team were thinking we should be able to integrate it across all possible weathers in the future, we thought we'll use a simpler model in which farmers gauge the degree of weather uncertainty by looking back at the weathers they've experienced over the last M time periods. So I'm thinking about what my weather uncertainty might be. I say, well, it was like that last year, it was like that the year before, thinking back on those and thinking, actually, that's a good sample of what the weathers might be. We also imagine that they have like a forecast of what the weather's going to be into the next period. We observe that because we've got the data on it for both calibration and for prediction, but the farmer is sort of thinking about it as a forecast. We think that, we're going to assume that the farmer attributes probabilities to each of those. So there's a probability that will be the weather from last year, a probability of the weather from the year before, and a probability of the weather they think is going to be my best estimate of what the weather is. And we have these rows of those probabilities. And again, for simplification, we're only going to try and use data to try and identify one of these probabilities. That's the probability the farmer attributes to the weather that's coming into the future, and all the others are going to be taken as equal. So 1 minus rho will give us those divided by the number of weather time series they're taking into account. So once we've got all that, we now have the objective function. What the farmer's trying to do is to maximize this, that's wrong, that should be this utility function, sorry about that, this utility function, that's right, sorry, this utility function, which is this, given those probabilities they're ascribed to, and they're choosing how to manage that particular parcel. Let's just get these out. So now we've got our model. It's expected utility maximization given uncertainty of the weather, given these different parameters that we've got in there. We have data to look at this. We've got, as Danny was saying, this DEFRA data with 3,000 farms. We've got this leaf area index, all of which are outputs of the model, so we can begin to calibrate this model to data. The things we're going to calibrate, and we've got quite a short set, there's lots of things you could calibrate, is we don't really know the qualities of the soil in each of our parcels. So this theta I is a parcel specific soil quality which we would like to learn about, and every time we're getting your data in about what farmers are doing, how they're managing it, we're learning about these parameters. We don't know the risk aversion parameter for the farmer. We don't know the probabilities that they're putting on these different weathers, and these are the sets of parameters that are being calibrated from this data using this underpinning model, and that's what Mohammed's going to talk about. Is that right, Mohammed? Good. And the dream is, as Danny said, that as we get these data series coming in year after year, the satellite data giving us how quickly the crops are growing, when they're being planted, we're going to be able to refine our understanding of each of those. How am I doing on time, Dan?
We got plenty. We're on 15 minutes.
Okay, that's good. That's the crop model. So now we have a model, once it's calibrated, which tells us how much profit and what food production we get from choosing different types of crop on each of the parcels. There's a second part of farming which we're going to model in roughly the same way, and that's a livestock management component. Again, we're simplifying. We're going to imagine that you've got a choice between dairy, beef, or sheep, or some mix of those. And each of those is defined by how much feed you need per head of each of these types and how much capital you need to look after them. So if you've got a dairy farm, you've got to have enough milking parlour space to be able to get milk out of them twice a day, every day of the year. Likewise, if you've got sheep, you've got to have enough barn space to bring them in the lambing season to look after them. If you haven't got that, you can't have the sheep. So we've got these capital requirements for each of these, and the feed requirements, how much grass and nutrients they're going to require. And we're making a decision over how many dairy, how many beef, and how many sheep to have on our farm. That's what we mean by the livestock choices, just like we're thinking about the crops. So let's just get that all up. Roughly speaking, you can divide up a farm's production of the feed for these types of animals into 4 compartments. One is rough grazing, and rough grazing is the sort of, imagine Dartmoor or something like that, but it's generally on poor soils. It's low nutrient grass types grow there. You don't fertilize this stuff. You're not managing it. It's not cut for silage, and generally you would never put a dairy herd on there. That's Chris's information. He's not shaking his head. It's just you have your high value dairy. You're not going to stick up on this rough grazing. If you think about all the fields where you see cows and sheep, that's usually called permanent pasture. And that's grassland, which is always in grassland. It usually has a mix of grass types. You often spread nutrients in it, often the slurry, the cow excrement that gets collected gets spread back on that as a nutrient, and that can be grazed. And often you graze it and you cut it and you store the grass from that in some sort of silage storage or silage clamp in order to feed your livestock during the winter months. Also, you can actively grow grass like it's a crop, and this is called temporary grassland. So you're planting it, sowing it, nutrients, cutting it maybe once or twice over a cycle, maybe more, and you could graze it and cut it. So we've got these 3 different types of grass. They're important, they're biologically different in so much as this tends to be sort of low nutrient grasses. This tends to be a mix of grasses with some of them higher nutrients, and this should tend to be sort of planting a particular grass type which is going to be high in nutrients because you're growing it to deliver feed. Right, so each farm is defined by the quantities of these different types. And we have a model, and this development is going to be really very similar to the development we've had on the arable. That's who said livestock there, so that's going to confuse you. So we have a grass yield model, and the grass yield model we're proposing to use is one called Mod Veggie. It's simplified, but it has most of the characteristics that we need. Again, it works at a parcel scale with a parcel scale of HI. For each parcel, you've got to define the mix of grasses that go in there. So if you're on your temporary grass, you've probably just got a single type of high quality grass, something like a ryegrass. If you're on your rough grazing, then the mix of grass, there's 4 different types of grass. You're one of the low nutrients, poor quality soil grasses will grow there. And if you're on your permanent grassland, you've got some mix, and these alphas are the mix of those 4 different types of grass that you would have on the pass. We can fix those. See, we haven't actually got to this bit. We can fix those, or we could attempt to learn them from the data. Again, we've got soil qualities, again, we've got weather, and we've got a set of management decisions this time, said Z, across the different types of grass, which include sowing date, but that's only if it's a temporary grassland where you sow, fertilisation possibilities, cutting and grazing intensity. Obviously, for certain sorts of grass, if it was a rough grazing, there's no fertilisation or cutting. If it's rough grazing, then your grazing intensity is only determined by the number of beef cattle you have, you're growing for meat, and the number of sheep you have, you're growing for wool and lamb, not by the dairy. Okay. And the outputs of this model give us the yields of grass, the quantity of food matter that we need. So the model progresses very similarly, but this time we're summing up across the different types of land that we've got, different types of livestock we've got. So we're making a decision over how many sheep, how many dairy, how many cattle we've got. We've got a price for those, a cost of raising them. This gives us our profits from a decision of over how many livestock of different types, indexed by L, we've got. Here we've got the costs associated with managing the different types of grass we've got. So these are the sowing, fertilisation and cutting costs. And we've also got a cost associated with, should have a C with there, the cost associated with buying in food. So if on our agricultural land, our grassland, you're not producing enough food, we can buy in supplementary food. If we're producing too much, we could sell that supplementary food. So our profits include the idea of buying in and selling on agricultural grass. This is maximised in our model subject to the constraints that we've got to get enough grass of suitable quality to feed the number of livestock of the different types we've got, and we might have to supplement with buying in stuff. Plus we've got these capital constraints, which means that given the amount of barn space, given the amount of dairy capital that we have, we can't put on more cattle or dairy or sheep than the capital. And our objective looks really similar. We're maximising a risk-averse utility function over uncertainty over the weather to make decisions about how we manage these things, which then determines our outputs and the quantities of.
Where's yield in the model? Yeah, but where does it go in the profit? I didn't see the D.
It comes in here. It doesn't come into profits. Because the profits all come from the selling of the sheep, which are fed by the nutrient constraint. I didn't write it out, it got a bit complicated. So we've got a nutrient constraint, which we're growing this much stuff. Calibration, probably we'll talk about this. We've got leaf area index for all these parcels, that's great. But that detailed data on grass, there is a data set that exists, which is being collected annually from Rothamsted of 50 farms on a weekly yield. If they'll release that to us using Rothamsted contacts, that would be great. So this grass check is a national data which would give us wonderfully detailed data on the productivity of different grasslands. We just have to see if we can get ourselves in on that. The calibration parameters, same as before, soil qualities for each place, farmer risk aversion, this weather probability, but also potentially we can either fix these, the different mixes of grass in each of these parcels. We could try and learn about these from data as well, because this will allow us to have a specific grass mix for each parcel. I'll skip that, and Mohammed's developed the technology which talk about the structure of this model is very similar to the one we've seen before. And Mohammed will talk about the arable management model. Now we've got the livestock model. Okay, that's our core. We've now got a structural model of how farmers make decisions about what to do on each of the parcels of their land, taking the grass and the different plots of arable. We've got that capability. The activity mix components then say, well, what should we do? Given for any of these parcels, I could evaluate what different decisions about that would give me in terms of farm profitability. I can start saying, what's the overall farm profits that come if I do this set of activities or this set of activities or all these other activities through to here? And the activity mix is thinking, well, what would be the best set of activities to do? So for any decision over a parcel activity, we can use these two models to tell us what the utility the farm would expect from a particular mix across the whole farm. And we're assuming they're going to choose that activity mix which gives them the best utility. How we do this, we're sort of starting to talk about the way the sort of farm model development side of the gang are thinking about it was to think actually there's a limited set of different combinations of activities that make sense, and we can narrow the space of combinations of activities across parcels reasonably well to some set that we could think about. There is the possibility that we might be able to exploit some of the technologies that Danny's preluded already, that I think people are talking about, certainly Bertrand, and be able to think across this entire space of combinatorials of different activities. We'll see how we get to on that. There are some issues still to be resolved, such as how we deal with the fact that once you decide to do something with crops, you usually have to run them in a particular order. But we have plenty of data from which to be able to calibrate this, because we know the activity decisions that are made across the country at the moment. Final decision is capital investments. We're breaking this down into some fairly simplified decisions over expanding effectively the capability I have for arable, the capability I have for beef and sheep, and the capability, this is a slurry bit, and the capability I have for dairy. So we're going to have a fairly simplified model of capital, but it will allow us to look at these important questions about moving between farming types. So in our old model, we used to be able to move from arable to dairy overnight. Now we're thinking there's a capital investment which makes these decisions to move between big farming types quite costly. And we're going to introduce the idea of stickiness, that there are costs associated with that switching. Again, we haven't parameterized that yet, but that's where we're going. So a model run. We've got this annual farm decision process, all that working together says, I've decided what capital I'm going to have and what activity mix I'm going to do. We do that every year. The capital decisions carry over from year to year. So any capital I've invested in is available to me in the next year, unless I disinvest from it. And to make this run out, we might use emulation and uncertainty. We've got some big things to deal with. One is this is set up at the farm scale. So we have this underpinning quite detailed model of how a farm will make decisions and how that might play out over time under certain drivers. But there are some questions we might want to ask, like national policies, which will involve us upscaling to do it for the whole country. That's difficult. We've thought of ways in which we might be able to pass across some of our physical parameters, soil parameters from one location to another. Farmer preferences, how we pass those across is up for debate. How we do this is difficult. Certainly it's going to involve some form of emulation to take this one model and take it to the millions of farms or hundreds of thousands of farms we've got. We might have to use some aggregation or representative farms approach to be able to use the farm model to say what might happen over an entire nation. I was told to do a little bit of research talk. I wanted to do a little bit. What if we had that capability? Then we'd not only be able to see what a particular farm did, but what the aggregate set of farms do across the country. Now that's quite important, and research we're doing under Net Zero Plus is showing us the importance of this. It's because if things tend to favour, say, wheat production, lots of people create wheat supply goes up, and suddenly the price of wheat drops. So we have these aggregate effects that when we start thinking about national policy are important to take into account. So we've got a model which we use, which talks about trade and how these prices would work. We've got, using the old farm model, we're able to say, given some sort of policies, what will happen to food production, but given UK food production, what happens to prices? It makes a huge difference. These are prices going up. This is what you would do with the land, all pasture. If you didn't take that into account, this is what you do. If you didn't,